Newton's second law gives us a relationship between the change in an object's motion, as represented by its acceleration, and the agent responsible for this change, as represented by the net force acting on it. The Work-Kinetic Energy Theorem provides another such relationship. In this context, the change in the object's motion is represented by the change in its kinetic energy, and the agent responsible for this change is represented by the total work being done on it. In this mini-lesson, we work through an example showing how to use the Work-Kinetic Energy Theorem to solve problems. First, however, let's briefly review the Work-Kinetic Energy Theorem. It says that the change in the kinetic energy of an object being acted on by a net force over a distance is equal to the work done by that net force. Or in equation form, 1/2 mv final squared minus 1/2 mv initial squared is equal to the total work. You may be wondering why we need another method for solving mechanics problems when we already have Newton's second law. Well, while Newton's second law is always valid, at least in classical physics, it is not always easy to use. This is particularly true for cases in which the net force, and hence the acceleration, is not constant during the motion. In these cases, energy methods, such as the Work-Kinetic Energy Theorem, often make hopelessly intractable problems rather simple to solve. But even in cases that are accessible to Newton's second law methods, work energy methods are often easier and quicker for the simple reason that they are scalar equations rather than vector equations. So there's little need to resolve vectors into components. Let's do an example. An extreme skier, starting from rest, coasts down a mountain slope that makes an angle of 25 degrees with the horizontal. The coefficient of kinetic friction between her skis and the snow is 0.200. She coasts down a distance of 10.4 meters before coming to the edge of a cliff. Without slowing down, she skis off the edge of the cliff and lands downhill at a point whose vertical distance is 3.50 meters below the edge. How fast is she going just before she lands? As always, we start by translating the words of the problem into a picture. Our job is to determine the skier's final speed just before she lands her jump. This problem is actually not all that hard to solve using Newton's second law to determine the skier's downhill acceleration, and then constant acceleration kinematics for the two consecutive segments of the problem. I encourage you to try that approach on your own, both for practice and so that you'll see how much easier and quicker the work energy approach is for this problem. We will solve this problem using the Work-Kinetic Energy Theorem. Here, the initial event is the skier starting down the slope, and the final event is the skier landing after the jump. Since she starts from rest, her initial kinetic energy is 0. So if we knew the total work done on her from the initial event to the final event, then solving for her final speed would be a simple matter of solving this equation for v sub f. You might be wondering, what about the mass? It's true that the problem doesn't tell us the skier's mass, but by now you're probably beginning to notice that the mass drops out of many mechanics problems. Will that happen here? Well, from experience, we know that the normal force on the skier, and hence the kinetic friction force, will be proportional to the skier's weight. Since normal force, kinetic friction force, and weight are the only forces present, the net force will also be proportional to the skier's weight, and therefore so will the total work. That means the m on the kinetic energy side will have an m on the total work side to cancel with. So we won't need to know the skier's mass. We'll see more about that in a few minutes. The total work done on the skier is the sum of the work done by gravity and the work done by kinetic friction. The normal force does no work here because the skier's motion along the ski slope is perpendicular to it. And we know that forces perpendicular to displacements do no work. The work done by gravity is always minus mg times the vertical displacement, delta y, regardless of the path taken. Kinetic friction obviously only does work for the skiing part of the motion, not the jumping part. Kinetic friction always acts opposite to the sliding motion, so that the angle between the force vector, which is uphill, and the displacement vector, which is downhill, is 180 degrees. That means the work done by kinetic friction is F sub k times S times the cosine of 180 degrees. Cosine of 180 degrees is minus 1, so the work done by kinetic friction is minus F sub k times S. Combining these two equations gives 1/2 mv final squared equals minus mg delta y minus F sub k S. We're given S, we know G, and we've decided that M will cancel. So now we just have to determine delta y and F sub k. The total vertical distance the skier traverses is h1 plus h2, where h1 is the vertical distance of the starting point from the cliff edge, and h2 is the vertical distance of the cliff edge from the landing point. The vertical displacement, delta y, is the negative of this distance because the landing point is lower than the starting point. The problem tells us that h sub 2 is equal to 3.50 meters. But we have to compute h1 from other information given in the problem. Since the skier skis 10.4 meters down a 25-degree slope, the vertical distance traveled is just given by trigonometry as h sub 1 equals 10.4 meters times the sine of 25 degrees, which equals 4.40 meters. Therefore, delta y is equal to minus the quantity 4.40 plus 3.50, which equals minus 7.90 meters. To determine the force of kinetic friction, we need a free body diagram. The skier's weight vector points straight down, as always. The normal force on her skis points perpendicular to the slope, and the kinetic friction force points parallel to the slope in the uphill direction. Its magnitude is related to the normal force by F sub k equals mu sub k times F sub n. If we resolve the weight vector into components parallel and perpendicular to the slope, and then recognize that the acceleration perpendicular to the slope is 0, we find that, when applying Newton's second law, the perpendicular component of the net force, which is F sub n minus mg cosine 25 degrees, is equal to the mass times the perpendicular component of acceleration, which is 0. Solving for F sub n gives F sub n equals mg cosine of 25 degrees. That means the magnitude of the kinetic frictional force is F sub k, which equals mu sub k times the normal force, which equals mu sub k times mg cosine of 25 degrees. Putting this all together, we find that 1/2 mv final squared equals minus mg delta y minus mu sub k mgs cosine of 25 degrees. Notice that the mass m appears in every term on both sides of the equation so that it cancels out. The answer does not depend on the mass, as we predicted earlier. Solving for v final, we find that v sub f equals the square root of negative 2g times the quantity delta y plus mu sub ks cosine of 25 degrees. Substituting in numbers and evaluating gives the skier's final speed, just before landing the jump, as 10.9 meters per second. Does this seem reasonable? Well, most of us probably have a better feel for speeds in units of miles per hour. So converting her final speed to these units gives 24.4 miles per hour, which does indeed seem believable.